My discussion is just trying to widen the concept of, widen people's perception of what modeling might be. Not necessarily what it is today, but what it might be and why it might be that. Why we might need to think about a wider scope. Developing software that understands the real world. Now, most of the software models we've discussed so far are basically models of the software. So it's like having a house, you model the house. The house is built because somebody worked out that there are forces of nature that create the need for a house to be the way it is. And because forces of nature haven't changed a lot, the houses, the models of the houses become the issue, not modeling why the house is the way that it is on account of the varying forces of nature. Now, if you take a house and you stick it in the ocean, and then you take it in Mars, and you go to various, and you put it on the sun, and places like that, you might find that the design has to be a little more flexible. So it's not the design of the house you're talking about, it's the design of the environment in which the house works. Software-wise, a simple example is that I can profile what I need to do if I want to buy coffee in Starbucks. But a better application for me to buy coffee in Starbucks would be, how am I getting there? Am I in a car? Am I driving while I'm handling something? So understanding the environment, modeling the real world in which I will be making that transaction or driving my car or something, becomes an issue. So modeling the world isn't so easy to avoid going forward as software becomes more fit for purpose and fits into our lives more. And as Christos said, it's the people that we're dealing with. People make software, people use software. And so when people use software, modeling the world that they're using it in isn't completely redundant. Back. Most software today, and most software, the history of software is that the challenge was to make a machine do anything. I mean, from abacus to machines taking cards and so on. The problem was that we had a problem getting the machine to understand us. It's still a problem today, but a lot of things have been covered, a lot of problems have been covered by developing languages that machines understand. But in the end, we tell machines what we want. That's what we do. We write the code in somehow understands the world, and then we give commands to machines. When we write the code, it's the commands to the machines that we're looking at. That doesn't tell us what we haven't told the machine. If I look at a line of code, it doesn't obviously tell me what's not there and which use case won't work. Something else has to tell me what won't work. I need a model of the world to tell me what won't work, not just what my code and what commands I'm giving to the machine. So we spent a huge amount of time and effort making having different languages. We say languages change every 6 months. Yes, the language we speak to the machine changes every 6 months. It's not the understanding of the world that changes every 6 months. That's not the part of the model that's changing. Let's see what happens.
Down, right.
Why does it have all these stuff? Okay. So it isn't that there aren't, UML, we mentioned UML a few times. UML gives you an entity relationship. It starts with an entity relationship. What entities are you talking about? I've never heard anybody discuss the world problems in terms of entities. I don't see Donald Trump saying the entity is this, and then that entity is related to the other entity, and there is a joint here, and people don't speak that way. So it's obviously UML, the entity ER concept that was used in UML and is considered a fundamental backbone, isn't really modeling the world, it's modeling the software. The main reason why we have entity relationships in databases is because you don't want to duplicate the data. We want to find the data and not duplicate it. Is that telling us how the world works? Is that telling us how a user thinks when he's using a handheld device? or what his preoccupations are, or how to arrive at a good user interface. No, it isn't. It's telling us how not to duplicate data in databases, how to retrieve it fairly quickly, how to have a language that retrieves it. It's not about the world. It's about how do we make the computer understand what we want. Okay.
Yeah, you can do that.
Here's a simple example. I mean, this is Jesse Jackson talking to Nelson Mandela. And he's asking a simple question: how is it? How is his life in jail? Christos's presentation will tell you that there's probably a theme behind this. Why is he asking Nelson Mandela about his time in jail? Probably because the average activist, like Jesse Jackson, doesn't want to spend half his life in jail. And if Nelson Mandela did spend half his life in jail, one would wonder what gave him that kind of motivation. So he'll ask him asking about his time in jail, but he's not really meaning that. He's meaning, what made you stomach spending so much time in jail, and why did you keep at it, and why did you, and in the end, how did you end up with a career that you have? We've got plenty of queries that we can run to find data in a data source, and Nelson could be thinking like this. But the truth of the matter is that he's probably got 1 million memories of his time in jail. He also knows from that the question that Jesse Jackson is making, that he doesn't want to know who he met in jail, or what he ate there, or which side his window was on, or whether the door creaked, or whether he could hear people being tortured. That's not what he's asking him. He's asking him, how did you stomach this? And this is the part that people in the audience would want to know as well. How did he do it? So if I want to be an activist, what's the difference in me and Nelson Mandela, more or less? So, even some of the queries here mention prison. Prison isn't going to give him. It could be, which is the closest prison to where they're sitting right there, or it could be anything. The point of the question that Jesse Jackson is asking is basically, how did you stomach all these years in jail? Now, there is obviously a model in Nelson Mandela's mind, and also in Jesse Jackson's, and these models are quite reasonably close so that they can have a conversation without taking ages to retrieve the right data. Now, that model exists. We can't avoid recognizing that those models exist. So that people do have models of the world in their mind. That's why, one of the reasons why it's so difficult to go from requirements to actual code in software, because people have a very rich model of what they're doing, and they both understand the model, and that doesn't translate directly because the computer doesn't have a rich model. When we start a computer program, often enough we write a few lines of code and end up the computer program says, "Hello world." What does that mean? That it understands the world, that it's greeting us, that it has feelings, that it doesn't mean anything. I mean, somebody wrote a command and it came up with a caption. So the concept of computers having models of the world is there, but it's not very well developed. And certainly no computer could emulate the conversation between these two people, because the knowledge of the world is so vast. So, we're trying to close those gaps, but the gaps, the model is this big, and the parts that we're addressing are small parts. For example, machine learning. Machine learning assumes that we've got correct, reasonable, and salient information to study, which means that we're getting ATM, let's say, transactions, or things that happen a lot, like people buying things in Walmart. And then we can learn about how one thing correlates with another. Now, that assumes a lot of things. In my business, when there's a problem with a machine, I remember 30 years ago, when we had to go at slow speed in the ships, we were creating problems on the cylinder liners. There wasn't going to be any machine learning that was going to tell us why that was happening, because nobody was studying the molecular structure of there was no sensors in the cylinder liners, there was nothing to tell us, nothing to study. So there wasn't the streaming data that was telling us things. Another side to put it, a lot of streaming data isn't telling us anything very interesting. For example, we can say that we're getting all the bank transactions. We don't know why people buy things. We don't know what they bought when, what their balance, what their the options were when they bought that. We don't know that. So we're studying this and making conclusions about it. Why don't we ask the guy, why do you buy this? That would probably get us a lot further in understanding why things are happening the way they are and the model of the world. So we do need machine learning. There's absolutely no doubt that there's a huge amount of value and there's data that we need to analyze. But we have to understand that it isn't making a model of the world. It is focusing on something, trying to work back to a model of the world that a lot of the time won't be very good. So, architects, mechanical engineers, electrical engineers will always have models. There's nobody builds this without a model. There's a model. It doesn't have to be a 3D model, but there's plans. There's things that tells you how things interact with each other. It's a model of the world. It's a simpler model of the world, of course, because the spatial relationships are easier to explain than, let's say, how Nelson Mandela came up with the answer to the question. That's not easy to do. It would take a computer program quite a bit of modeling in order to understand what kind of memory structures Nelson Mandela has about his jail time and why the other guy was asking him the question. So practically speaking, if we're going to start programming tomorrow on a new program and that your boss told you that this is the application he wants, when do you think you'll need some modeling? Well, when there are many exceptions to rules. When you write rules, those rules don't end up in, don't translate directly to code. The rules don't write the code. So if you've got lots of rules, you're going to have to make sure that they all work inside, and you've made those into good algorithms. There's a lot of them, there's a big problem. And if they interact a lot, then you have to break them down into separations of concerns. This separation of concerns is almost impossible to do without models. When there are variations in processes, it's a similar thing to exceptions to rules, but I have a process that I need to send something here, I have a process I need to send something there. I have a process where I don't know where I need to send it. I have a process where I need to send it somewhere, and later on I need to know where to send it. These variations to processes make the logic very, very specific. And so you have tons and tons of logic. If you haven't got a structure or a model of this logic, it's going to be very difficult to test. It's going to be very difficult to evolve. A lot of scheduling systems that tell you, let's say, when a pilot can, when it's good time to call this pilot because he'll be next in line to fly this plane, those models are very difficult to maintain because they have so many parameters in them. So predicting behavior of situations, again, to predict the behavior of a situation, you need to know how those processes are converging towards a goal. If you don't have a model of the goals, it's very difficult to do that. If you're in a software company, and as Christos mentioned, the maintainability, when complex logic needs to be extended or maintained, how are you going to extend or maintain logic that's broken up into pieces that don't give you a clear propagation path? So you don't know that when I add this, it's going to affect that. It's not going to affect that. Why do we have regression testing? Why do we spend 50% of development time testing? Because we don't know what the software is going to do, because there's no model in the software. There's no model in the logic. There's a model in the database, and that's mainly there to make sure we don't write things twice in the database. The most important part, and Fabio will be able to tell us this, give us his opinion on this, when you need logic to be easily scrutinized by other stakeholders. you could say that I've got, I'm compliant with GDPR because I just got a certificate and some bloke came over and said that I've got nice procedures with GDPR. That doesn't mean that if it's mission critical and if my information can then be copied on 1,000 sites somewhere that I can never trace back, that this is satisfactory for a major stakeholder. A major stakeholder may want to know exactly how are you sorting this problem out with your sensitive information. What exactly do you do? How is it stored? How do I see how it works? How do I see how it doesn't work? How do I know where the weak points are? If I don't model this, it's going to be very difficult. I can't read your code. You can't read your code. You can't be sure. If we could understand the code, we wouldn't do regression testing. This is a small car, and you might think if it runs into something, it's no big deal. But cars can and will run into things unless somebody's making sure that the logic behind whatever is making this drive by itself is valid for all the situations that might come up. How do you know what all the situations are? You have to make a model. How do you make sure, how do you scale the validity of that software? You have to compare it to something. How do you compare it to something if there's no structure involved? So you can have documents and rules. Rules will be fine, but in the end of the day, the guy who's certifying this, the person that is responsible and will end up having to answer for people being hurt by these things running into each other, that person has to show his methodology. What did he check? How did he check it? So it isn't just that I'm writing code and I'm writing logic and it's fine for me and my customers. It's there's third parties that are involved, and there's high risks involved. And we're moving into that era very quickly for one reason or another. This is just a small caption or small diagram on the right here, on the left here is, let's say, an ERP system. It stops around about where those, not where the tables are, the red tables, but just above that. That's the extent of, let's say, a legacy system. And that legacy system is giving us permission to go and read people's personal information. Okay, now the personal information isn't in that system anymore because we have GDPR and we don't want to have it in the same place that we have our normal code. So what we have is the ERP system. The blue dots on top of it, I'll tell you what they are in a minute. On the left-hand side, in the dotted box here, we have a secure area. And what is the secure area? The secure area is a place where the information, which is at the bottom, that's the personal information down there. That personal information is in a secure area, meaning it's not in a conventional software system. It's embedded in a chip, and it'll take you a long time to hack into it, let's say, because it's not, and there's no conventional means of accessing. There's a model on top of it that tells you, that releases that data when certain parameters arise. And on top of that is a stakeholder who's making sure that your model and your system satisfies the requirements. So he could be a stakeholder like an insurance, who says, I'll insure you because I know you've got this embedded in this system here and that people can't hack into it. Somebody can't send you a virus and shut down all your terminals and also access this information. It's not there. And then the middle part here is monitoring. It's actually doing something else as well. It's easier to do with the model. It's not impossible to do without the model, but it's damn hard. And that is, it's modeling under what conditions you should be asking for that secure information. So you have a system down here that, let's say, has crew member records and their medical records, which is something that we do in our company here. But under what circumstances are you asking for medical records? Is it saying somebody come in and just ask for medical records? Or does he have to have done certain transactions in the system in order to qualify the fact, oh yeah, this is a guy who needs the medical record? Because to to get the medical records, you have to be considering sending this person to the doctor, or you're recruiting him and you want to make sure that he complies with your health protocols. So you have a model on top of the other underlying software. Now, why do you need a model? You need a model because in order to model behavior, that this happens before then in this session. If I only use transaction records to see that, I noticed that you were in the system then and you accessed this part of the database. That's very good, but how do you know it was me that did that? And how do you know that while I was doing that, I wasn't doing something else, or what I was doing before? In order to string together happy path transactions, let's say, which are legitimate transactions to access the secure data that is down here, you have to model it. It's not going to be easy if you don't model it. Certainly not going to be scalable, and certainly nobody's going to be able to understand and check and make sure that hundreds and upon thousands of these systems are going to work. This is why I'm saying that we're coming up against a wall where we will need to do modeling. This is just an example of a model looking at. It's not easy to read. But basically, scheduling, it's telling you that in order to schedule something, there's certain separation of concerns. First of all, what are you scheduling? Some sort of resource, usually. So you have to match the demand to the resources. So some part of this is matching people to jobs, let's say, in a dry dock situation. You might be matching machinery to jobs. So do you have enough machines in order to do this job? After that, you're concerned with how long things take. Before you schedule things, you have to know how long things take. There is an enormous amount of logic behind how long something takes. It depends who's working on it, how quick they are, what the weather's like, what the equipment, how good the equipment is, and whether there's, and so on and so forth. So durations that affect scheduling are very much separate from matching, let's say, the resources, so that the job and the resources match at that time that you want to start with, that you want to start the work. Then you've got the issue of interrelated processes. A lot of processes don't go together. For example, you can't have the same person working on two processes if it's not in the same place, and they can't switch over from one to the other. So you have to build constraints into this. Now, if you've got a system where you can actually see what the model is, you can use, this is not a very good depiction, but again, I'm just trying to tell you how models might be thought of. You want to see how these things interact. These things are interconnected. There's other connections behind them, so that you know that the duration of the time that it takes the job affects the job by 5%. The real issue is what can't you do at the same time with this job. That's what's really telling you your scheduling constraints. Also, the duration of the time that you need the people. You're saying you have a pool of 10 people. Well, what happens if your duration is 2 days long and you still have those 10 people? There's a huge separation in concerns, which in a model you can see. If you put this in an algorithm, it's going to be very hard to see. On this side here, you can see the code. The code is actually adjacent to the data. This is a data model and a code at the same time. So you can see the logic. It's not clear here. And here's the basic difference. The basic difference is that in conventional coding, you're asking for information in tables. The tables don't give you a unique idea of the field. The tables together give you a unique idea of the field. But when you process that in the code, and you say, I want to convert this order quantity to that order quantity, it doesn't tell you where to pick up the data. It's a different language that we're using to pick up the data and show it. Why? Because the databases that we use, the models of data, do not give first-class state to each attribute. So we can't build a model out of it because the model isn't continuous. So we have two models there. Ideally, what we would like is a model where all the states, you notice those little green dots on top of those squares. The square is just the data, and the green dot is the state. If you can give first class status of all the data points in your database, then you can build a model. And you can see that you can say that yes, now I'm propagating from along the red line, and this is the code conversion that's telling me that I should change my quantity from 2 to 3. But I've got first class. My model understands with my locations, my database, and it gives me the code, which is written conventionally. It doesn't have to be written in any language you like. So that's it for me. Any question?
The question of modeling is 30 or 40 years old, at least for software.
Software and about 10,000 years.
Goes back 1,000 years, of course. The problem that we have today is how to translate from the model into code and back. And have you solved this problem? Is it because
No, that's not the problem.
I didn't follow the development.
Well, I disagree that that's the problem, but yes, it is being done. But I disagree with that being the problem. It's not the problem. That's the problem if you think that coding is your obstacle. If you think that the coding, I noticed that when Christos made a diagram, that coding is like 1% of the time. I would say it's perhaps more if people aren't procrastinating. So is it really that we want to save the time of the actual coding, or do you want to save the time of modeling and getting understanding between people about what the constraints are? So if I asked you, how would you build a scheduler, would you be able to explain to me and I could go and build it? Or would we have to sit down and make a model of it? So the question is modeling the world a challenge or translating model commands into code? Because it's not that difficult and it's being done in general. It's not very sophisticated modeling, and it's not, but the question is, why are we trying to save the coding if the coding isn't the reason why we get things thrown back at us? I don't think that what Christos mentioned was that the actual coding that was the problem. It was the planning of the coding, the understanding of the requirements, the understanding of the user, the understanding of the maintenance issues, the understanding of the interconnecting platforms. How's that going to help me if I've got different platforms in an installation? How is the fact that I've got a way of writing code or a canned way of writing code, and there's lots of work done in that direction, how does the automated code help me when my problem is understanding what functioning environment I'll have at my client site? So don't I need to model my client site? Wouldn't I need to say that this attribute here is working with that system over there? So when it's working with that system, I have a different, I need a different rendering mechanism. I need a lot of different tools, and it won't work with this contraption. It won't work with that handheld device. This is the modeling of the real world I'm talking about. And no, they don't. The development of the other side is not such a big challenge. It's being done, and again, because of the notion that, oh, we have huge problems coding. No, we don't have huge problems coding. We have huge problems passing our ideas, what we coded, the 10,000 lines of code that nobody can read, that tell us that the system gets stuck, and why IT managers are sitting in banks 24 hours a day, hoping that the thing doesn't fall down, and taking hours to figure out why it did fall down. Because we don't understand the code. It isn't the writing of the code that's the problem. The problem is that we haven't structured a way of communicating what it is that we've coded.
Coffee break now after that?
Sure. Thanks very much.